the dead load. Yep, let's call that self-weight. Any other loads?
It's connecting the two edges together.
It is connecting those two edges together. So what I hear you say is that perhaps this one was made a bit long and that one was made a bit short. There's a fabrication internal stress in there. Let's go with that. That's what you meant.
Yeah.
Internal stress. Yeah, others?
It's gone over something, so there's room for the wind to go.
Wind load. Yep. If you doubt wind loads can affect the bridge, there's a lovely video in this topic for you guys to look at called the Tacoma Narrows Bridge. It's probably the most famous bridge disaster in the world. What are the loads on that?
Oh, when it rains?
Rain, yeah, water. So, and I'll give you free snow. Okay.
Would like heat also be a load because like it changes the strengths of different elements of it?
Let's separate them out. I'll put thermal loads in, but you just said it changes the strength. That is on this side of the equation. So let's hold that thought, very good thought, for now. Okay. So just considering the loads. So we've got person, self-weight, internal stress, wind load, water, snow, thermal. Let's put earthquake in. Sorry? Yeah. I'm going to add one more. I call the idiot load. I'll come back to that. All right. What we do is we look at these loads and we classify them. And the first most obvious one we start with is the self-weight. And we call that dead load. Okay? Dead load is the self-weight of the structure. You cannot remove the dead load because it is the structure. Okay? So anything that's there, the thing that's there, and anything that is absolutely permanently attached to it. Okay? So in this case, we'll be looking at the self-weight of that beam. We'll be looking at the planks that go across the beam like that, or whatever the decking is. Okay? That's our dead load. If we have, let's also talk about a house that or a building that we're designing at the moment. If you're talking about the roof, the beams, the sheets on the roof, that's dead load. Okay. If you have a permanently installed ceiling like we do here, the ceiling's a dead load as well. There's the ceiling hanging off the roof. Okay. All right, then we go to live load. Live load is anything that can be on there and might not be on there. Okay? So strictly speaking, wind is a live load, but we treat that separately. Water is definitely a live load when rain falls on it. When rain falls on this roof, you're going to get at least a few millimeters of water on the roof before it can drain off. When you get snow, snow can collect on the roof. We'll leave internal stresses out for a minute, but most of those others are live loads. Okay? Wind is treated separately, like I say, so we'll put a W for that. And snow is treated separately. Thermal is treated separately. EQ is its own thing as well. Okay. As engineers, we look at complicated data like that and we think, how much do we actually have to consider and how much can we ignore? And this is where a bit of engineering judgment comes in. Okay? This is a suspension bridge with this beam right here. And you know when you've been on a suspension bridge, it sways and shakes. Okay? If the world here is swaying and shaking, how much do you think that plank is going to be concerned about that? Not at all, right? Earthquake, we can ignore earthquake for a suspension bridge. What earthquakes do is they impose a deflection on something. So if you have a really flexible structure, it just moves with the earthquake, it's not really a problem. When you have stiff structures, that's when earthquakes are really a problem. okay? In early days in structural engineering, you can ignore a fair bit of earthquake loads, okay? Obviously, don't take that to heart. You have to consider them at some stage, but not here. Snow load, yeah, we don't know where a bridge is. Let's say it's in the middle of the outback, there's no snow there, so happy days, we can ignore snow load, all right? The person load, if you go to AS 1170, it will say in a situation, what sort of load you have to have on a structure. So it's normally expressed in kilopascals, as in, you know what a kilopascal is? Is 1,000 newtons or 1 kilonewton on 1 square meter, okay? 1 kilonewton is about 100 kilos. So I weigh approximately 1 kilonewton. And if 1 kPa, it means I occupy 1 square meter, okay? So if we look at the loading in this room, if everybody is spaced out on a meter grid, that would be a live load of about 1 kilopascal. But you can imagine that actually you might get situations where more people are packed into this room than that. So this room is going to have a load requirement somewhat higher than 1 kilopascal. It's going to be at least actually four or five, okay? If you look up AS 1170 for a bridge, you'll see that it's actually a suspension bridge like this. It'll be 1 person, 1 kilonewton per meter length of it, if it's a single file type bridge. That's not a figure that everyone carries around in their head. I just happen to be designing one a bit like this at the moment. So that means that there's a person, theoretically a person could be there, there could be another person there, a meter away, another person there, etc. And the bridge gets loaded up. But on this particular plank, let's say that's a meter wide, it has a zone of about 1 meter, it's got about a kilonewton on it. All right. So we isolate that beam and we draw it like that. And it's held up at the ends, and it's got a load pushing down on it, which happens to be 1 kilonewton per meter, okay? So we've just taken that beam out, and we said how strong does that beam need to be? And we're working that out now. All right, what we do though, is we exaggerate these dead loads and live loads. And if you look in the AS 1170, the formula is in there about how you want to do it. And it is the load action equals 1.2 times dead load plus 1.5 times the live load. So someone asked the obvious question. Anytime? Why is it 1.2 and 1.5? Why are they different? Is that the obvious question? Yeah. Yes? I hear a yes. Anyone want to agree with her? Sure. All right. I can't find the correct bit. Here we go. Opposed actions. Here we go, yes, combination of actions. If you go to 1170.0, in section 4, it says for combinations that produce a destabilizing effect, E, which is the effect, is 1.2 G and 1.5 Q. Dead load is often written G, and live load is often written Q. Okay, why are they different? The reason is because we know a lot about the dead load. All right? All good? We know a lot about the dead load. We can have a look at that beam. We can weigh it. It's pretty obvious what it is. All right? We've got a lot of control of the dead load. The live load is a bunch of hooligans who come and they stand on the bridge. We do not know as much about the live load. So we're more careful about that. So we exaggerate the live load 50% more. We exaggerate the dead load and 20% more. All right. Okay, and wind, we'll talk about the wind ultimate load, and you can add these other things to it later, okay? So that's equation you should probably commit to memory. You'll use that a lot, all right? On any particular thing, 1.2 times the dead load plus 1.5 times the live load. Now there are subtleties and exceptions to that. For example, if the live load is something that pushes up and the dead load is pushing down, they work in opposite directions. So in that case, you go 0.9 times the dead load and 1.5 times the live load. Or 1.2 times dead load and 0.9 times the live load. If you get all the directions, you get what I mean there? Don't worry about it. If they're going in opposite directions, these factors change. But basically for gravity, that's your kind of factor there, all right? So that means, and now when you multiply it like that, that is called an ultimate load, and it's an ultimate load, it earns the star. All right? We all good with that?
Yep.
Okay. Now, let's go to our capacity. And the capacity is really specific on what the thing is, okay? So in a, whoops, that's not good. If we had a beam like that, and there's our dead load, and I draw a line like this to indicate distributed load, right? The load actually might be a point load. In fact, if it's a person on there, the load might be a point load which lands right there. Or it might be a point load which could be moving anywhere, moving point load, okay? Or it's a distributed load. You have to do